Welcome to 3.2 logarithmic functions and their graphs. By this time, most of you have worked with logarithms. Those of you in A2PC, perhaps not. That might almost be an advantage because you've worked with them and you can perhaps what I might refer to as you can do logarithms. You know, we can work with equations in them, maybe be able to graph them. But every year when I ask classes what is a logarithm, even though they've been exposed to them before, I don't get too many that really have a grasp of what a logarithm is. This is going to be question number one on the Chapter 3 test, is going to be what is a logarithm. And if you understand, or if you understand the definition I'm about to give you, which is a little bit different than the book definition, a lot of the properties that we're seeing right below here should make sense to us. So what is a logarithm? A logarithm is an exponent. A logarithm is an exponent that turns its base into its argument. And holy cow, sorry about that. Sorry about the focusing. We're going to get that taken care of. Just looked back at my screen and saw I wasn't focused. I believe we got it now. What is a logarithm? A logarithm is an exponent that turns, it's a bad looking N, that turns its base into its argument. For instance, we might have something like this. Log base 2 of 8 equals 3. Log base 2 of 8, this, which is equal to 3, is an exponent. So 3 is the exponent that turns the base into the argument, is the thing we put into a function. 8's the argument here. So this means that 3 is the exponent that turns 2 into 8. It's another way of writing exponents. There's a lot of advantages to using logarithms in a lot of real-world problems. So when we look at that definition of a logarithm, I want this. I want that to be known. I want it to be understood. I don't expect that we necessarily understand that yet. But they have their definition of a logarithm here. But let's look at the properties. Log base A of 1 is 0. So that logarithm equals 0. So that 0 is the exponent that would turn A into 1. Oh, A to the 0 equals 1. These things are synonymous with one another. Log base A of A equals 1 because my phone's just going to keep going off and going off. So I will be right with you. Log base A of A, that of means it's going into a function. We're thinking this is going into the function. Log base A is 1. Well, this thing, which is equal to 1, is the exponent. 1 is the exponent that turns A into A. 1 is the exponent that turns A into A. And this is kind of a weird one right here. Log base A to the x. Well, this is so simple if we understand our definition. This says that this, which is equal to x, so x is the exponent that turns A into A to the x. Well, no kidding. I don't even really necessarily need to understand what they're saying here. This is because A to the x equals A to the x. X is the exponent that turns A into A to the x. And this last rule is a little bit different. This says if log base A of x equals log base A of y, then x has to be y. Logarithmic functions are 1 to 1 is basically what that thing is saying right now. Okay. Now natural log is just like, natural log is the same as log base e, but it's used so often that we just have a special name for it, natural log. We just call it ln. ln1, lne. So this is like saying log base e of 1 equals 0, because 0 is the exponent that turns e into 1. Log base e of e is 1 because 1 is the exponent that turns e into e. And log base e of e to the x is x because x is the exponent that turns e into e to the x. And likewise, these are 1 to 1. Okay? So you can look at the definitions, but the definition I am looking for is exactly this. A logarithm is an exponent that turns its base into its argument. So write the logarithmic equation in exponential form. So we want exponents. Well, log base 8, or log base 16 of 8 is the exponent that turns 16 into 8. So we have an exponent that turns 16 into 8, and log base 16 of 8 is it, and that's equal to 3/4. So 3/4 is the exponent. Well, let's take a look at that. That's like saying the 4th root of 16 to the 3rd. But the 4th root of 16, 2 times 2 times 2 times 2 is 16. This is 2 to the 3rd, or 8, sure enough. Okay. All right, and then you'll have some problems where you're doing that in reverse. Well, take a look. 3/2 apparently is the exponent that turns 9 into 27. 3/2 is the exponent. What are logarithms? Logarithms are exponents that turn their base, the base of this is 9, into 27. No, thank you. No, thank you. No, thank you. I'm recording right now. Bye-bye. Thank you. Okay, sorry about that interruption. Let's continue on. You're good. Bye-bye. Let's see. Use the definition of logarithmic function to evaluate the function at the indicated value of x without using a calculator. So we're supposed to find log base 16 of 1/4. Sorry, a little bit distracted by that interruption here. Okay, so use the definition of logarithm. Well, if I said this is x, this would mean 16 to the x. So x is the exponent that turns 16 into 1/4. Now, hopefully I recognize 16 and 4 both as base 2 numbers, but they're also base 4. This is like 4 to the second to the x equals 4 to the negative first. 4 to the second being 16 to the x, so that's 4 to the 2x equals 4 to the negative first, so 2x equals negative 1 and x equals negative 1/2. All right, take a look at this one. Wow, this looks kind of bizarre, but if we read this right, we're going to say x is the exponent that turns 3 into 3 to the negative 5. The logarithm is x. X is the exponent that turns 3 into 3 to the negative 5. Or what is the exponent that turns 3 into 3 to the negative 5th? Well, negative 5 is. Okay. Let's take a look at this. What is the exponent that turns 4 into 4 to the 3rd? What is the exponent that turns 4 into 4 to the 3rd? This is equal to 3. What is the exponent that turns 4 into 4 to the 3rd? This whole logarithm is just 3. But right here, this is saying log base 4 of what equals log base 4 of 4 to the 3rd. Well, that x must just be 4 to the 3rd. That's because of this rule right here. If two logarithms of the same base are equal, the arguments are equal. Okay, still rattled by that interruption we had there, and still going on a little bit. Hopefully I don't have to pause. But anyway, let's take a look at 27 or 26. For some reason I skipped it. So this says we want to find log base 10 of 100,000. So this is the exponent that would turn 10 into 100,000. What is the exponent that turns 10 into 100,000? Well, this is a base number. I'm going to go 10 to what? 10 to the x equals 10 to the, let's see, first, second, third, fourth, fifth. Therefore, x must be 5. Okay, here's some problems that mess with people from time to time. Let's take a look at our exponent here and let's talk about it. This exponent, just the exponent, we would say what? We would say this thing is the exponent that would turn 6 into 36x. This thing is the exponent that would turn 6 into 36x. Well, guess what that thing is? That thing is an exponent on 6. It's like this. That's this guy's purpose. This is the exponent that works on 6's. And this thing is working on a 6. And what does it do? It turns it into 36x. That takes some marinating time for a lot of young math students, but we're certainly going to be talking about those problems quite a bit. Okay, let's take a look at 40. Sure, we can read this log base 4 of 16, but that's not how I'm thinking of it. I'm thinking of this as 1/4 times the exponent that turns 4 into 16. 1/4 times the exponent that turns 4 into 16. What is the exponent that turns 4 into 16? Be a lot tougher if this is what is the exponent that turns 4 into 17, but the exponent that turns 4 into 16 is 2. And we get 2/4 or 1/2. Okay, kind of a big section here. We might cut this into 2, but I'm going to just try to power through this. We're only about 12 minutes in right now. We'll see where we are. I might have to make this 2. But here we go. Find the domain, the vertical asymptote of the x-intercept, the vertical asymptote, the x-intercept of the function, and sketch its graph by hand. Okay. So why are the exponents that turn 10 into this x minus 1? So what we would do is we want to pick values of x, but there are going to be some trouble spots for us here. See, 10 raised to a power has to be x minus 1. So I want to choose values, and I wish I wouldn't have written that right here. I'm going to go back and just cover this up. I want to choose values for x. Follow me here. This is something new, and it's a technique that I really like for these purposes. I want to choose a value for x. I want to subtract 1 from it, and then I want to take log base 10 of it. The key here is after I subtract 1, I would like this number, the number that's in here, to be a power of 10. And what are my powers of 10? Well, 10 to the first is 10, and 10 to the second is 100. I'd like, after I subtract 1, for this to maybe be 100. So I'd choose x to be 101. I'd like x maybe to be, or x minus 1 to be 10, because log base 10 of 10 is a breeze. That's the exponent that turns 10 into 10. The exponent that turns 10 into 10 is 1. But what value do I have to choose for x? So here's what I do. I'm just going to refer to this portion of my little chart I'm making right here as the bus. It's bus shaped. What's driving the bus? The engine, log base 10. What values do I want to go into here? I want powers of 10. I'm going to start, you'll see what I'm doing here. 1/10 is maybe not the most convenient power of 10, but it is most definitely a power of 10. 10 to the negative first is 1/10. 1 is a power of 10. 10 to the 0th is 1. 10 is a power of 10. 10 to the first is 10. And I can put 100 here. 100 is a power of 10. I could put 1 over 100. Okay. This is, so then after I get to this spot, you'll follow what I'm doing here. I know this is a little bit bizarre right now. If I put 1/10 into here, what's the exponent that turns 10 into 1/10? Negative 1. What's the exponent that turns 10 into 1? 0. What's the exponent that turns 10 into 10? 1. What's the exponent that turns 10 into 100? 2. Okay. Now, I choose a value from x, then I subtract 1. But remember, in order to get a value of 10 in here, I had to choose 11 for x. So as I move, if I call this row A, row B, row C, as I move from A to B, I subtract 1. So as I move backwards, I need to add 1. In other words, I have to have, I'll do this one first, I have to have 2. 1 plus 1, 2. If I put 2 in here, I get 1, and finding the log base 10 of it's easy. Add 1. 1 and 1/10. A little weird. 1 and 1/10 minus 1 is 1/10. Oh, I love 1/10 in log base 10 because the exponent that turns log base 10 into 1/10 is just -1. I'm going to choose 11 here. I'm going in reverse. I'm adding 1. I'm adding 1. I'm going to choose 101. So if I choose 11, it gets turned into 10. We take log base 10 of 10 and we get 1. If I choose 101 for x, I get 100. What's the exponent that turns 10 into 100? 2. So here are my ordered pairs. I want to point at 1 and 1/10, -1. Wow, that's tough. 1 and 1/10 just barely past there gets me the -1. And I want to point at 2, 0. And I want to point at 11, all the way out at 11. It's going to be all the way out. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's going to be all the way out here before I get up to 1. So this graph wants to look like this curve. And you notice it really flattens out because I have to go all the way out to 101 just to get up to 2. Now, definitely worth pointing out. If I choose 1 for x, I get log base 10 of 0. Is there an exponent that will turn 10 into 0? 10 to 0 to the 0th is 1. 10 to the positive is a positive. 10 to the negative, let's see. Oh, 10 to the negative is 1 on 10 to the. 10 to the -3rd is 1 on 10 to the 3rd. No, I can't get 0 out of there. I can get really close to, I can put really close to 0 in here, but x minus 1 may not equal 0, therefore x may not equal 1, and we have an asymptote right here. And this graph would chase down that asymptote. That's going to take some soaking time too, and we're going to need to practice some of those. Unfortunately, we're going to do it right here. So let's follow this chart. I'm going to choose a value for x. The next thing we would do is add 1. The next thing we would do is take log base 10. And then after that, this is all order of operations, I'd add 2. The key is I don't really want to choose values for x plus 1. I want to choose the values that go well into log base 10. And those values are 1/10 and 1 and 10 and maybe 100. Maybe 1/100th, maybe 1,000, maybe 1,000,000. Those are all powers of 10, but it's these three that typically we're going to be able to build around. The exponent that turns 10 into 1/10 is -1. 10 into 1 is 0. 10 into 10 is 1. And 10 into 100 is 2, if it would fit on the graph. After I come out of log, once I'm done with that, I add 2 to it. I find out what my logarithm is, and then I add 2. So plus 2 would be 1, plus 2, and plus 2 would be 4. But to get from row A to row B, I add 1, but I'm going backwards. I actually need to subtract 1. This would be -9/10. This would be 0. This would be 9, and this would be 99. Take a look. If I, for instance, choose 9 and put it in here, I get log base 10 of 9 plus 1, log base 10 of 10. Oh, that's the exponent that turns 10 into 10. That's 1. And then I just have to add 2 to it, 3. So when I put up 9 on when I choose 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, the graph is up 3. And when I choose 0, the graph is up 2. And if I went out, it would take all the way out to 99 just to get up to 4. So this graph really flattens out. When I choose -9/10, I'm up at 1. But maybe the most important thing to note here is that x plus 1 has to be greater than or equal to 0. Can't be 0, so x may not be -1. And we have a vertical asymptote at x equals -1. Just like up here, we had a vertical asymptote of 1. X can't quite get to 1. All right, we're going to come back down to this, wrap up the graph on that for a minute. Let's make certain we've answered all of our questions here. Find the domain. So the domain, the graph doesn't exist until I get over to 1, and it truthfully doesn't exist at 1. So our domain starts at 1, but I believe is going to continue on to infinity. How about x-intercept? The x-intercept, that was a nice clean one. We found the x-intercept when we put in, and that's back to this chart right here. We found the x-intercept when we put in 2. The x-intercept occurs at 2. Okay? All right, so we have a vertical asymptote here. So this graph wants to get sucked right into that asymptote. It never quite gets there and looks something like that. The domain is a breeze. The domain would be anything to the right side, anything just to the right of -1 on forever. The x-intercept, that's a whole different story. I got to find out when this crosses right here. I suspect for our purposes right now, we could set y equal to 0. Let's go ahead and do this. I probably should have given myself a little bit more room here. I apologize if you don't have the room here. If I go 0 equals 2 plus log base 10 to the x of x plus 1. If I look at that, I'm going to go log base 10 of x plus 1 equals -2. Let's think in terms of our definition of logarithm. -2 is the exponent that turns 10 into the argument x plus 1. So this is x equals 1 on 10 squared minus 1. X equals 1 on 10 squared, or x equals 1 on 100 minus 1, or minus 100 100ths. It equals -99 on 100. Wow, that's tough. X-intercept, -99 on 100. Okay, believe me, we're going to get some practice graphing these things. Okay, so use the graph of y equals log 3x. Well, what is the graph of log base 3 of x? Let's take a look here. Y equals log base 3 of x. I can't put 0 in for x. We just talked about that. If I put 3 in for x, that's a great value. Put in 3, what's the exponent that turns 3 into 3? 1. If I put in 1, what's the exponent that turns 3 into 1? 0. And my next good value would be 9. I'd go all the way out to 9 before I get up to 2. So here's my asymptote. That's what a logarithmic graph looks like. That's what log base 4 of x is going to look like. It's just going to take till we get up to 4 to get up to 1. That's what they all look like. So we're supposed to use the graph of y equals log base 3 of x to do a match. And this looks just like it, except, well, let's start with this one. This appears like it has an asymptote over here. So I'm looking for -1 to be a pretty interesting value of x. It looks like, or maybe this is a backwards situation, or excuse me, 1. I'm looking for 1 to be a pretty interesting value of x. Let's just go with that. 1, yeah, I guess it's all right. 1's okay. 1. That would be an indication of our asymptote. Okay, do we have any others where we're 1? Now, what else is different about this one? Well, the graph is backwards. Does that support it? Would we expect? Sorry, I'm not pointing at it here. I got to zoom out. A little bit on the fly here. So we have an interesting value. Our asymptote is shifted to the right one, but the graph is backwards. That's kind of what it looks like here. Backwards, and the MIVOX is 1. So this is A. How about B? B has the same asymptote, so I don't think it's shifted right or left, but it does look like it's a little bit higher. Like at 1, tough to tell here. If this is 5, I don't know, 1, 2, 3, 4, 5. It looks like it's shifted up a little bit. Any of these look like they're shifted up? There's a post function plus 2. I'll bet this one's B. What's the big difference with this one? That one, compared to this, it still has the same asymptote, it appears, but it most definitely looks like it's upside down compared to that graph. And there it is. There's C. We should have a graph that looks like it's shifted to the left 2 and upside down. Left 2 and upside down. And there we have D. Okay, just like the last section, I'm not interested in you going ahead and sketching these. I just want to know, in fact, it doesn't even ask you to here, how does this graph differ than that graph? We have plus 7 as a pre-function. That affects the X. That's a 7-day head start. So everything happens sooner. Or the MyVox is negative X, or is negative 7. That is 7 to the left. In this case, log base 2x looks just like log base 2x, but here we're subtracting 3 post function, down 3. Here we have pre-function, MyVox is 1, so we are right 1, post function, up 4. Okay, we should be, that is what we specialize in. Okay, 61 to 68, write a logarithmic equation in exponential form, for example. Well, we don't need an example if we know this. What is a logarithm? It's an exponent that turns its base into its argument. 0 is the exponent. The base is e, so the base of my logarithm is e, so that's ln. You could put log base e, but just isn't considered proper. ln. And e gets turned into 1. So it's log base e of 1 equals 0, or ln 1 is 0. How about this? Can we write this without the fraction? 1 on e to the 4th is the same as e to the negative 4. And that equals some irrational number. So negative 4 is the logarithm, which is log base e, ln, and I'll have people do this from time to time. It doesn't bother me, especially as you're learning. We'll get away from, we would hopefully move away from that. So the logarithm is turning its base e into this, and that logarithm is negative 4. So 0.0183. This says this logarithm, negative 4, is the exponent that turns e into 0.0183, turns its base into its argument. Again, this takes a little bit of soaking time for us, but we'll be in good shape with it. We'll spend some time next week. We got a guest speaker coming in, perhaps, for some of you, if this is 2017 and you're looking at this. But lots of help will be provided, and then we'll certainly spend some time with some questions and answers on this in class. All right, in exercise 81 through 88, use the properties of the natural logarithms to rewrite the expression. Okay, now we need to look back at some properties. And our properties include, boy, it's almost like that doesn't belong right here. Use the properties. And our properties I did not include on here. Okay. Those properties, one of the properties says this. If I have a log base b of c, that could be written as log base b of c to the a. For right now, I just want you to accept that as fact, but that will definitely be an explanation that we go through. That's one of the properties. So this means that this could be written as negative 1 times ln of e could be written as ln of e raised to the negative first. It could also then be written as ln of e on 1, or 1 on e. You know what? I think I'm misinterpreting this right now. We don't need that. We can just simplify this. Let's just simplify this. -1, forget about what I just said here because I believe that's in the next section. I apologize, kind of scrambling to get this video ready for you. ln e, that's log base e of e. That means this is the exponent that turns e into e. What's the exponent that turns e into e? Well, e to the first is e. Let's go ahead and zoom in on this. E to the first is e, so the exponent that turns e into e is just 1. And we get -1 times 1, -1. Okay, so again, I won't normally do this, but I'm going to write this as 7 log base e to the 0. I want you to think about just that for a moment, the way I would read it, and see if you can interpret what that is equal to. This is the exponent that would turn e into 0. I wonder what the exponent is that would turn e. Wonder what the exponent is that would turn e into e to the 0. See, asking this question of somebody who's well versed in logarithms would be like asking a 8th grade math wizard what is 7 times 43 divided by 7. It's pretty clear to him. What's the exponent that turns e into e to the 0th? Of course it's 0, so this is 7 times 0. Okay. All right, 86. I'm going to think of this as e to the, again, I wouldn't normally do this, but we're just learning this. Read this the way I would. Yeah, we can say log base e of 22, but we can also say this is the exponent that turns e into 22. It's kind of like this guy's living its life for one purpose. My purpose in life is to be an exponent on e and turn it into 22. And just wandering around in the wilderness trying to fulfill his destiny. If only I could be an exponent on e, then I could turn the e into 22. Well, guess what? It is an exponent on e. So listen closely. The exponent that would turn e into 22 is an exponent on e. Guess what it turns it into? 22. Check it on your calculator. Okay, how about this one? ln. I'm going to call this e to the -4th. Same thing. Or if you like, log base e, because we're just learning, of e to the -4th. If we read this instead of in log language, but the definition of log, we would say this whole thing is the exponent that turns e into e to the -4th. What is the exponent that turns e into e to the -4th? Well, -4. Okay. All right, more graphing here. LNs. This is not the most convenient. Remember we said in class e for our purposes for graphing is about 2.7. So for graphing these, here's what I'm going to do. I'm going to choose a value for x. I would add 1 to it. And then I would take ln, or log base e if you like. And we're going to say for our purposes, no, e is not exactly 2.7, but I mean, how are we going to graph 2.7 anyway? It's just an estimation. So we're going to say it's 2.7. So values I'd love to be here. I'd love to have, and I'm going to put this one over here, 2.7. After I add 1, I'd love this to be 2.7. Well, if I added 1 to get 2.7, what did I start with? I have to subtract 1. 1.7 gives me 2.7-ish, or roughly e. And what is ln e? It's the exponent that turns e into e. That is 1. And then I'd like 2.7 squared here. Whatever that thing is. I'll go ahead and grab a calculator and check that real quickly. 2.7 squared. Clear, second quit. 2.7 squared is about 7.3. So if I can get 2.7 squared, what's the exponent that turns about 2.7 into about 2.7 squared? That is 2. What did I have to start with before? Well, since this is about 7.3, you can check it on the calculator if you'd like, about 7.3, I needed to start with about 6.3. I needed to subtract 1. Let's plot those points. 1.7 gets me up to 1, roughly. 6.3, 1, 2, 3, 4, 5, 6.3 gets me up to 2. So my graph's taking on this kind of a look. We know it flattens out as it goes on. What would be another good value to put in log base e? 1 would be. Because what is the exponent that turns e into 1? 0. But to get 1, I have to choose 0, subtract 1, put in 0, get out 1. What's the exponent that turns e into 1? 0. So 0, 0 is a point on the graph. So we're just building this guy as we go. And I could do a 1 on 2.7. I wouldn't mind this to be 1 on 2.7 because what's the exponent that turns 2.7 into 1 on 2.7? Negative 1. Okay, but let's talk about this. X plus 1, we know it may not equal 0. So x may not equal negative 1. Asymptote, I think I'm pretty comfortable with how this graph looks. Gets sucked into that asymptote, it doesn't escape. All right, let's see what we've got. Find the domain. So our domain is not quite allowed to put negative 1 in, but anything bigger than that seems fine. Find the x-intercept. Oh, the x-intercept was convenient. The x-intercept occurred at 0. There it is. Put in 0, get out 0. Logarithmic sketch this graph by hand. Verify you can definitely check that on your calculator. Okay, so let's take a look here. We may actually want to start with this. 3 minus x may not be 0. Therefore, x may not be 3. Can you take a second and think about just right now the domain of this graph? The knee-jerk reaction might be just based on the last ones that it must be all to the right of 3. But this graph is backwards. I'm going to claim right now, you don't have to do it in this order, believe me, but I'm going to claim the domain is anything from negative infinity till 3 I expect is good. Okay, so let's show you how I do this. I'm going to choose a value for x. The next thing I'm going to do to it is multiply it by negative 1, then add 3 to it. Then I'm going to take ln. So a little bit different look to this. This is the key. I want, after I go through the multiplying by negative 1 and adding 3, I want those values to be 1 and 2.7-ish and 2.7 squared-ish, which we said is about 7.3. I could have 1 on 2.7 here. But that's what I want after I'm done choosing an x, multiplying it by negative 1, adding 3. So I need to go back there. To get from row B to row C, I had to add 3. I need to go back. I need to subtract 3. So I get negative 2. I subtract 3. I get negative 0.3. I subtract 3. I get 4.3. To get from row A to row B, I multiplied by negative 1. To get back, I divide by negative 1. Or multiply by negative 1, as the case may be. So this becomes 2, this becomes 0.3, and this becomes negative 4.3. Okay, what is the exponent that turns e into 1? 0. E into e, 1. E into e squared, 2. Let's plot our ordered pairs. 2, 0. 0.3, 1. Negative 4.3 gets me up to 2. And I believe we've got a graph that looks like that, and we're approaching our asymptote right there. Okay. All righty. And our 3-2 assignment is right here. I expect that we're going to get a lot of that hammered out in class time, but this one's going to take a bit of time, and again, going to take some. For a lot of people, logarithms, it takes a while to understand them, but every time you see a logarithm, every time you see something, let's say log base 6 of 42, you're going to say this is the exponent that would turn 6 into 42. You know what I know right now about that? If I say this is x, this is the exponent that turns 6 into 42, I know that 2 is less than x is less than 3, because 6 to the second is 36 and 6 to the third is way more than 36. Or excuse me, is way more than 42 even. Way more than 42. All right, so this is the exponent that turns 6 into 42. X is the exponent that turns 6 into 42. So that way, as we move forward, we're going to have a better understanding if we're thinking things that way. The graphing can be a little bit tricky. There's a lot of problems in here that are going to be quick and straightforward, but the graphing can be a little bit tricky. Okay, we will be in this for 2 days, but in 2017, the first day of this is going to be an in-class work day after you've taken these notes. Should be tomorrow. Hopefully you've done this. All right, good luck with that, and we will see you soon.